Welcome to the Worldwide Center of Mathematics Musimathics Fourier Analysis video. In this video, I'll be going over the logic and reasoning behind both the discrete and continuous Fourier transform, as well as their applications to signal processing and digital music production. When you think of math and music, Fourier analysis is probably one of the first things that comes to mind, especially if you have some calculus background. There are two primary concepts from Fourier analysis: Fourier series and the Fourier transform. There are two types of transforms: the continuous Fourier transform and the discrete Fourier transform. In case you're interested in the more technical aspect of the Fourier transform, the continuous Fourier transform is found by using the following formula. Capital S of f, the transform, is equal to the integral from negative infinity to positive infinity of the input function s of t times a complex exponential e to the negative I times 2 pi ft dt. The transform takes a time domain input and returns a frequency domain output. Similarly, the discrete Fourier transform is found by using the following formula. Capital S of f with period 1 over t is equal to the sum from n equals negative infinity to positive infinity of the input function s of n times e to the negative I times 2 pi fn capital T. Just like the continuous Fourier transform, the discrete Fourier transform takes a time domain input and returns a frequency domain output. So you may be wondering why we even care about any of this. Well, the idea behind a Fourier series is a desire to represent complicated input functions in a simpler way. In fact, every function, especially relatively well-behaved functions, can be represented as the discrete sum of sinusoidal functions. These sinusoidal functions are scaled to best represent the original input function. It's kind of like the idea behind Taylor series, if you're familiar with that concept from calculus. Now you might say, wait a minute, I don't remember seeing a single sine or cosine in either of those formulas. Well, you did in fact, but they were kind of hidden. There's something called Euler's Formula, which you may be familiar with The Simpsons, that allows us to express sinusoidal functions, or sines and cosines, using the following formula. Sine strong looks terrible. Okay. E to the it is equal to cosine t plus I sine of t. So the formulas I showed you before really do contain sines and cosines. Fourier analysis has many applications in music as well as in mathematics and physics, including one that is especially relevant to our everyday lives: digital sound processing. Say, for example, you're given a single musical note or pitch. Taking the Fourier transform of that input pitch allows you to see all the component frequencies that make up the note you hear. This also works in the other direction. Specifically, you can compose component frequencies together digitally to recreate the original sound. This is how electronic music is produced and also explains how digital sound processing works. Whereas we use the Fourier transform to deconstruct input music samples, we use the inverse Fourier transform to synthesize frequencies to produce sound electronically. An instrument or sound's timbre can be analyzed using the Fourier transform as well. When we take the discrete Fourier transform of some sound sample, the resultant components represent frequencies from the sound's harmonic series, which we discussed in a previous video. Say, for example, we have the sound samples of a flute playing in A and a trumpet playing in A. If we take the discrete Fourier transform of both of these samples, we will end up with the frequency spectrum for both instruments. The ratio of each component harmonic frequency is what gives each instrument its timbre. In fact, the discrete Fourier transform of a clarinet sound produces a frequency spectrum very close to that of the human voice, making the clarinet sound actually like a person humming or singing when it's played. What you're looking at right now is the frequency spectrum for an acoustic guitar string. We can also use Fourier analysis for what is known as chord detection. In the previous video, I talked about statistical analysis of chord progressions in music. However, logistically, it would take an incredibly long time to analyze and categorize all the chord changes in a large body of music. Not to mention it requires music theory training and a lot of patience. However, we can use a technical computing program like MATLAB to determine, using something called the fast Fourier transform, all the constituent notes in a chord played in a sample input, and therefore identify the chord that is being played based on the identification of the chordal tones. Although this process is not 100% accurate, it significantly simplifies large-scale harmonic data collection. That's all for this video. To see the next video in the Musimathics series or visit centerofmath.org, click right here on the blackboard. Thank you for watching.